Hello everyone. Here I want to talk about nuclear energy. Nuclear energy is the highest energy density source known to humankind. A kilogram of coal can run a 100-watt light bulb for about 4 days, while a kilogram of natural uranium can run it for 182 years. Nuclear fission energy has emerged over the past 40 years to become a reliable base load source of clean and economical electrical energy. The issues such as rising air pollution, limited land area, and considerable variations in wind and sunlight make nuclear energy the most attractive option to overcome the shortage of energy sustainably. Also, among low-carbon electricity generation resources, nuclear occupies second spot. At present, there are 444 operable nuclear reactors worldwide, with 395 gigawatt electrical capacity, which is about 10.5% of global electricity generation. Moreover, there are 52 nuclear reactors under construction that will add 52 gigawatt electrical to the existing capacity of the operable nuclear reactors. There are two reactions of nuclear. The first one is fission and the second one is fusion. Nuclear fission is the process of splitting a nucleus into two nuclei with smaller mass. Just like the description before, fission means to divide. Remember that fission has two s, therefore it splits into two parts. Only large nuclei with atomic number above 90 can undergo fission. Products of fission reaction usually include two or three individual neutrons. The total mass of the product is somewhat less than the mass of uranium-235. A chain reaction is an ongoing series of fission reactions. Billions of reactions occur each second in chain reactions. On Earth, nuclear fission reactions take place in nuclear reactors, which use controlled chain reactions to generate electricity. Uncontrolled chain reactions take place during the explosion of an atomic bomb. The products of nuclear fission reactions are radioactive, but the energy released from this reaction is less harmful to the environment than the use of fossil fuels. The products are intensely radioactive and must be treated or stored. Nuclear fusion is the combining of two nuclei with low mass to form one nucleus of larger mass. Nuclear fusion reactions are also called thermonuclear reactions. Nuclear fusion produces less nuclear waste than nuclear fission, and the materials are easier to obtain. Nowadays, nuclear power plants divided by two types: pressurized water power plant and boiling water power plant. The first we're gonna talk is pressurized water power plant. Heat is produced in reactor due to nuclear fission and there is chain reactions. The heat is generated in the reactor is carried away by the coolant circulated through the core. The purpose of the pressure equalizer is to maintain a constant pressure. This enables water to carry more heat from reactor. The purpose of the coolant pump is to pump coolant water under pressure into the reactor core. The steam generator is a heat exchanger where the heat from the coolant is transferred onto the water that circulates through the steam generator. As the water passes through the steam generator, it gets converted into steam. The steam produced in the steam generator is sent to the turbine. The turbine blades rotate. The turbine shaft is coupled to a generator and electricity is produced. After the steam performing the work on the turbine blades by expansion, it comes out the turbine as wet steam. This is converted back into the water by circulating. The feed pumps back the condensed water into the steam generator. And here is the boiling water reactor. The water is circulated through the reactor where it converts to water-steam mixture. The steam gets collected above the steam separator. The steam is expanded in the turbine which turns the turbine shaft. The expanded steam coming out of the turbine is condensed and is pumped back as feed water by the feed water pump into the reactor core. Also, the downcoming recirculation water from the steam separator is fed back to the reactor core. In this section, we compare with advantages and disadvantages of nuclear power plants. As we can see, the plus points of nuclear power plants are less required space, the only plant source which can meet increasing demand of electricity at a reasonable cost, and use much less fuel than a fossil fuel plant. However, high maintenance costs and the treatment of radioactive waste should be the next focus in the future world. Talking about radioactive waste, it had been classified as two levels, high level and low level. The example of high level waste is used nuclear fuel and the low one are more to equipments like cooling water pipes, radiation suits, etc. High level waste need to be disposed carefully, embedded in concrete, and stored deep underground for thousands of years. It's a different case to low-level waste. Just store it in storage facilities and the radioactivity will fall to safe level in 10 to 50 years. Here are a short review about the latest development of nuclear technology and materials. Development of an outlook of advanced nuclear energy and technology. The vigorous development of nuclear energy is greatly constrained by economic factors in open electricity market. Furthermore, issues such as the supply of nuclear fuel, the disposal of nuclear waste, and the prevention of nuclear proliferation pose new challenges to the new sustainable development of nuclear energy. How to consider the three aspects of nuclear fuel, nuclear waste, and nuclear non-proliferation as whole, the world's nuclear energy community is exploring and developing advanced nuclear energy technology. Generation 4 International Forum or GIF selected 6 candidate reactor technology for further research and development. However, IAEA or the International Atomic Energy Agency have participated in the work related to the fast reactor project, including fast reactor design, fast reactor structural material, safety of liquid metal fast reactor simulation, and so on. In addition, a lot of research and development and application exploration on small modular reactors, including fast reactors, molten salt reactors, high temperature gas cooled reactors, have been carried out. Nuclear Energy Agency or NEA launched the Nuclear Energy Innovation 2050. The NI 2050 covers a wide range of technical fields including reactor system design and operation, fuel and fuel cycle technology, waste management and decommissioning, and non-electrical application. NI 2050 focus on aging management and long-term operation, severe accident knowledge and management, decommissioning technology, advanced fuels and materials, advanced fuel recycling, advanced manufacturing and construction, nuclear heating and cogeneration, hybrid energy system, and waste management and disposal. In summary, in order to actively cope with global climate change and to achieve the carbon dioxide emission reduction targets required by the Paris Agreement and explore nuclear energy sustainably, and so on. Various international organizations and major nuclear energy countries are exploring the advanced nuclear energy technology and promoting the demonstration of safe and reliable advanced modular small reactors. Actively carry out the research and development of the Generation 4 nuclear energy system and the International Nuclear Energy Cooperation. Here are the future outlooks of advanced nuclear energy technology. First, convert fertile material into fissile material in order to achieve nuclear fuel sustainability. Second, focus on the comprehensive application of advanced small reactors and the innovative application of advanced nuclear energy to build an efficient, low carbon, and flexible smart energy system. And the third, strengthen the best research and common technology research and development. The next one is material for nuclear reactors. This picture shows evolution of nuclear power reactors, which classified into different generations from Gen 1 to Gen 4. Gen 1 reactors were developed during 1950 to 1960s and used natural uranium fuel and graphite moderator. Magnox reactor is an example of Gen 1 reactor. This reactor got its name due to its use of magnesium alloy as fuel cladding tubes. All Gen 1 reactors are now decommissioned. The current fleet of nuclear reactors operational in the USA and elsewhere in the world are Gen 2 reactors, while Gen 2 reactors are essentially Gen 2 reactors with improved safety features. Gen 4 reactors are significantly different from Gen 2 and Gen 3. Gen 4 International Forum Down selected 6 reactor technologies out of 130 reactors concepts that are still at research and development stage and not expected to be commercially available before 2030. Here is the key component of nuclear reactor. As you can see, there are fuel cladding tube, moderator control rod, coolant, reactor pressure vessel, steam generator, and containment. And here is the presence of different surface conditions. Stress, water, temperature, and radiation leads to a few commonly observed aging and degradation modes of material operating in light water reactors. The next one is evaluation of LBB characteristic of candidate materials for main steam line piping in Korean nuclear power plants. Leak before break design concept, or LBB, is to the main streamline piping in secondary system of Korea standard nuclear power plants had been studied. The microstructures, mechanical properties, and consequential LBB margins of five candidate materials SA335 GRP11 or P1222, SA50 SA508 GR3CL2, SA508 GR3CL1, and SA508 GR1A steels were evaluated, and strong weak points of candidate materials for applying MSL piping were analyzed through the comprehensive analysis including microstructure, mechanical properties, LBB margin, usage history, economics, and so on. Three SA508 GR1A steels were used in RCS piping of OPR1000, and they were labeled A1, A2, and A3 according to the manufacturers. The SA508 GR3CL1 and CL2 steels used in the reactor vessel and steam generator vessel were labeled C1 and C2 respectively. Although C1 and C2 have not been used for piping materials in NPPs, their characteristics were analyzed together to compare the mechanical properties. SA335 GRP11 and P22, which were used in the main steam line piping of AP1000 and the main feed water piping of OPR1000, were labeled P1 and P2. Here is the optical microscope images of the specimens. The microstructure of SA508GR1A steels consisted of ferrite, perlite, and bainite. The grain size of the specimens were different depending on the manufacturer. That of the E1 specimen was coarse, while the A3 was fine. The microstructure of SA508 GR3CL1 and 2 steels was bainite. SA533 GRP and 11 P22 were composed of dual phase of ferrite and perlite. And here is the conclusion. The next is cold spray technology in nuclear energy applications, a review of recent advances. Cold spray technology is promising solid-state, powder-based deposition method for fabrication of coatings, near-net shape manufacturing, and component repair. In recent years, this technology has been investigated for many applications in the nuclear energy sector. CST or cold spray technology is a solid-state material deposition process, where micron-sized feedstock powders particles are propelled by pressurized high-velocity gas towards a substrate, where upon impact they form a coating. Here is a schematic diagram of cold spray process. In Fig A, the acceleration of powders particles supersonic velocity is achieved via preheated gas flow through a converging diverging level nozzle system. Above a certain particle velocity, strong adherent coatings are deposited from on substrates due to very high turn rate plastic deformation of particles and associated adiabatic shear instability at the interparticle and particle substrate interface. However, in Fig B shows material jetting at the interface and localized heating at and in the vicinity of the particle interface due to high velocity impact. Here is the direction of cold spray coating. Here are the example of microstructure of oxidized chrome coated as zirconium alloy at 1030 tenths Celsius temp. The oxidation kinetics for the cold sprayed chromium coatings were comparable to those of bulk chromium samples, indicating that cold sprayed chromium coatings were very dense. At elevated temperatures, interdiffusion at the coating substrate interface resulted in formations of chromium zirconium intermetal compound layer, which is exhibited of diffusion controlled growth kinetics. Cold spray technology or CST is an attractive approach for depositing coatings and near-net shape manufacturing due to its low heat input and preservation of microstructure of feedstock powder in the coating without oxidation or phase transformation during the deposition process. This paper presents recent advances in the use of CST for variety applications in the nuclear energy sector, including corrosion resistant coatings for fuel and structural components in current like water reactors, manufacturing of advanced fuel cladding tube in advanced reactors, and function coating for storage. And the last one is effect of soaking time at 1100 Celsius on the morphology and thermophysical properties of CaO Fe2O3, simulant material for nuclear reactor. Here the effect of soaking time at constant heat treatment temperature. The porosity of material is higher at 1100 Celsius for 1 hour soaking time, but it decreased with increasing soaking time at the same heat treatment temperature. Because of agglomeration particles, the agglomeration particles in the material increased with increased soaking time at constant HTT. This was happened due to formation of new paste at higher temperature. And the next one is effects of soaking time and constant heat treatment temperature on composition on material throughout sample. When material is heat treated at high temperature, the material has required lower heat for diffusion. When the material was heat treated at high temperature, many unstable phases are taken place. Due to this change, the properties of material will alter. The activation energy of CaO Fe2O3 would decrease after heat treating. The activation energy of CaO was calculated using the Arrhenius equation. Specific heat capacity of material is the heat requirement to increase the temperature of 1 Celsius of 1 gram of material. This study was carried out to know the thermal stability of material binary mixture. Okay, that's all. A little explanation about nuclear technology. If you all have some opinion about this topic, comment down below. Thank you and see ya.